really confusing. So if this is overwhelming to you, I understand. Take it one day at a time, learn what you can. A nonpolar covalent bond, they share the electrons equally, okay? They don't, like if you're, I don't know, splitting a spaghetti noodle with somebody, like in Lady and the Tramp, that movie, you both get the same amount of spaghetti noodle, okay? One person doesn't eat 3/4 of it and somebody get a fourth. You share equally. As a result, chemically, when covalent bonds are nonpolar, you can see the lines here are straight. They're not curved in any way. So all of these are non-polar covalent bonds, equal sharing of the atoms. This is hydrogen gas, this is oxygen gas, nitrogen gas, and this is methane, as I discussed before. Opposite to that is polar covalent bond. I like to think of a polarizing person. They just kind of distance themselves. They're polarizing. Unequal sharing. Okay, that spaghetti, somebody shares it, but they take most of it. Okay, water is the best example of this. Here, water, of course, is H2O. Here's the oxygen represented by red, and the hydrogen is represented by the white here. And see how instead of being straight across from each other, HOH, they're kind of curved up, kind of like ears on a mouse. It kind of looks like if my head was oxygen, if my hands were the hydrogen. If they were equally shared, it'd be like this. But since they're unequally shared, they're up there. And this gives water the ability to do some cool things in the body because of this type of bond. Because of this polar covalent bond that water has, it gives oxygen a little bit of negativity, and it gives hydrogen a little bit of positivity, which will come into play with our next type of bond. Hydrogen bonds. Okay, so here's a water molecule, here's another water molecule, here's another, here's another, here's another. And like I said, because of their polar covalent bonds, oxygen's slightly negative and hydrogens are slightly positive. Because of that, positive attracts negativity, right? Water molecules can then bond with each other. Here it is, right there. They're bonding, bonding, bonding. And in every bond, you see a negative oxygen bonding with a positive hydrogen. A positive hydrogen, negative oxygen, okay? These little dotted lines represent hydrogen bonds, okay? Hydrogen bonds, I like to use the example of a zipper. They're weak interactions, okay? 5% is strong as covalent, but they're convenient. They can form easily, just like it's easy to zip up a zipper, or they can break easily, just like it, unzipping, zipping, unzipping. Hydrogen bonds, like you think of ice. When you freeze water, it can become ice, easily forming those tighter bonds, and they can also loosen easily or break when they melt. Here is another example of what hydrogen bonding can do in water. It can hold big proteins, large 3D molecules together, like hemoglobin, together in their formation, their globular formation. And in water, for example, here's an insect walking on water. Hydrogen bonds enable that insect to do that. It creates something called surface tension, and this is how humans can walk on water. No, just kidding. We can go over that later. How far we are here. Okay. So we stated this before. Metabolism is the sum of all the chemical reactions in your body, and they're happening constantly. There's a law of conservation of energy, meaning the total mass of reactants has to equal the total mass of the products. Energy can't be created or destroyed. It just changes forms. So the food that we put in our body has energy, okay? Our body uses that energy and distributes it, the molecules in here, into our body. So chemical reactions are simply bonds being broken, like breaking up the bonds in here and reforming them, moving the electrons around, breaking those bonds. Bonds contain potential energy. Here are example of a few different types of energy. Energy is simply the capacity to do work. I have energy, so I have the capacity to do work. And they transfer in a chemical reaction. So kinetic energy, energy in motion. Potential energy is energy stored by matter. Due to object's position, like this car has potential energy once it's up there, or it's potential energy that's stored in chemical bonds. This apple has potential energy for me. Reactions can either release energy, chemical reactions, or it requires energy to do that. This will release energy in my body, exergonic. While you're catabolizing food, or not cannibalizing, but catabolizing, when your body's breaking this down, it's releasing heat, which is energy. The bonds are going to break, and your body's going to use it to make something else. Speaking of making something else, that's called endergonic reaction. When my body makes or enlarges my muscles, for example, if I lift weights, that's going to require energy added to be able to do that. ATP is the energy needed to do that. Activation energy is just the energy needed to start that chemical reaction. You've probably heard of it before. The energy needed to break those bonds so the reaction can start. And here you can see on the graph, there's the activation energy. Chemical reactions. Things that cause a chemical reaction. So here's atoms flying about, okay? Chemical reaction happens when they bump into each other, okay, in your body. Boom, 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 chemical reaction. So factors that cause a collision or a chemical reaction to take place or more likely to take place, one example is temperature. If you increase the temperature, these atoms are going to move faster, okay, and they're going to be more likely to react. That makes sense. Or if you add more fists in here, if you add more reactants, if you add more salt to your water, it's more likely that chemical reactions are going to happen. So increasing the temperature or adding more reactants can cause more collisions. Also, adding something called a catalyst. A catalyst is a chemical compound that speeds up that chemical reaction, makes it happen faster. And how it does that, let's go back to our graph. See the activation energy? How much energy is required for that chemical reaction to start? A catalyst will cut that, maybe in half or even less. So it'll happen quicker. Catalysts are enzymes, which we'll talk about in a little bit, but they can be used over and over to make chemical reactions happen in your body. They're not consumed nor produced in a chemical reaction. So they can be used over and over again, recycled, reused. So a catalyst, how it works, it helps orientate colliding particles so that a reaction can occur at a lower collision speed. It doesn't lower the number of reactants or products or anything like that. The difference of potential energy between them, it just lowers the amount of energy to start it. Here are just some different examples schematically of what chemical reactions look like. A synthesis reaction is in which your body makes something. It synthesizes something, also called an anabolic reaction or anabolism. Anabolism, okay. A plus B produces AB. That's just an easy way to remember it. Hydrogen plus hydrogen plus oxygen produces H2O. Decomposition reaction, so breaking it down, also called catabolism, okay? Breaking down something. AB produces A plus B. Pizza goes in your mouth, you chew it up, your body digests it into protein, carbohydrate. It's more detailed than that, but just so you get the idea. Exchange reactions, AB plus CD equals AD plus CB. Mix it around the atoms. Reversible, some reactions in your body can go both directions. You can produce something and then change it back. And produce something and change it back. And just make sure here. That is the end of part 1.